Hi all. I wish I could be with you right now, but I'm down in class in North Carolina. I'll be back soon. I'm only missing a couple classes. So I figured I'd pre-record some of the stuff that we'd be covering while I'm gone. Feel free to email me with any questions you have. Miss Witt is also a great resource for you. And even though we're starting a new unit, most of what we're covering is totally review. So I'm hoping that in these next 2 weeks we'll get a more solid understanding of some of these topics, a really comprehensive review, and some extra practice with some more difficult topics. So we're going to start with power functions. And what that means is that I have a monomial function, which is one term, mono meaning one, and it's written in the notation of f of x equals a times x to the n. And so I'm taking a variable x and I'm raising it to a power. So this is known as a power function. And this may look a little confusing, but what this means is that I have a coefficient or a number out in front, and this can be 2 or it can be negative 612, and I'm multiplying that by x to a certain exponent. And we're just going to look at positive exponents for the next few examples, but those exponents can also be negative. And the only rule that we're following here is that a does not equal 0 and n does not equal 0. And the reasoning for that is that if a equals 0, it would be f of x equals 0 times x to the n. The whole function will equal 0. And if n equals 0, so if I have f of x equals a times x to the 0, the whole function will be equal to a. Because remember from our monomial rules, or power rules, is that when I'm raising anything to the 0 power, it equals 1. So this would just be a times 1, which equals a. So we're not going to be using those as examples. And so this is a monomial function, which means it's one term. I'm not writing anything like 3x squared plus 2x plus 2. These are just our simple, basic monomial functions. And you guys have already graphed quite a few of these in your parent function graphic organizer and worksheet. And the first one that we're going to start with is the constant function. And this is written a little differently than normal. It's written as f of x equals c, but what that means is that f of x equals a number. So I can write like f of x equals negative 2. And what that means is that for every value that I put in for x, y, or the function value, is always going to be equal to negative 2. That is curved in true fashion of my art ability. So it's going to be a straight horizontal line across. So this means I have the same y value for every x value across the board. And this is still a function, remember, because it passes the vertical line test. Our next power function that we're going to look at is the linear function. And so this is f of x equals x. And remember that this is the same as x to the first power. So this is an odd power. This is still a power function. My coefficient here would be 1. My exponent would be 1. And so remember that I draw this just as a horizontal line with a slope of 1 passing through the origin. And so this extends from negative, negative values all the way up to positive, positive values. The next parent function or monomial function that we're going to look at is the quadratic. Remember that this is y values that are greater than or equal to 0, because I'm not going to have a negative y value for any of these. So I'm going to draw this. It's that classic U shape like that. That doesn't extend into these negative y values, because remember that when I square a negative number, it becomes positive. So all my y values are going to be positive for this. I then have my cubic function, which passes through the origin again, but it's more of a squiggle, so I have this point of inflection at 0, 0 here. X to the fourth, or my quartic, sorry that this got a little bit erased, my quartic function, it may seem a little intense to have an exponent of 4, but what this means is that I'm still raising it to an even power, so I know that I'm only going to have positive y values, because anything raised to the second power is going to be positive. I can have a negative value if I raise it to the third power, like -2 times 2 is positive 4, but times -2 again will give me -8. But then if I multiplied it by itself one more time, or 4 times, I'd get a positive value again. So I know my y values, or my function values, are all going to be greater than or equal to 0. But what's going to happen to these values is that they're going to raise at a steeper rate than they would in the x squared function. And you can do this out on your own. So if I have x to the 4th versus x squared, let's say I want to plug in 2 for these. If I plug in x equals 2, I'm going to have y equals 4 here, versus x equals 2 for x to the 4th, I'm going to have y equals 16. So that's a big difference. So this is increasing exponentially greater than x squared. And the same is true for x to the 5th. So it's going to look similar to my x cubed function, so my cubic function, but it's going to be narrower. I'm going to be making these values, it's going to increase more steeply than my x to the 3rd function, but it's still going to cross through my origin here and have a squiggle line like that. So if those are confusing, please go back. The constant, or the linear, the quadratic, and the cubic are all in your graphic organizer. The only new ones here are the quartic and the quintic. And what you have to remember here is that with the even exponents, I'm going to be extending in the same direction, or I'm going to have limitations on my y values, versus with my odd exponents, I can have negative y values. So this leads us right into symmetry. So just like I said, when I have an even power, I'm going to be symmetric about the y-axis. So symmetric about the y-axis. And you guys saw this in the parent functions. So you saw this when I had x squared, or x to the 4th. It was a U shape like that, and it was symmetric over the y-axis. This is different than an odd power that is symmetric about the origin. And we spent a long time doing this a few months ago. So we did our even and odds, but now we're relating it to powers. So this is symmetric about the origin. We spent a long time on these, and we didn't really relate them to powers. But we were talking about even or odd functions and how to prove them algebraically, how to prove them graphically. And so my odd powers, with the exception of my linear power, will be crossing the origin like that. So it's symmetrical. If I was to rotate it 180 degrees around the origin, that would be my odd power symmetry. And throwing back to end behavior, so remember when I'm describing end behavior, I'm describing what's happening when f of x, or what's happening as x approaches infinity and x approaches negative infinity. So what's happening to the function values when I'm approaching those with x? And so sometimes, like with the reciprocal function, I'm not ever going to approach those values. But for most functions, this is how we're defining end behavior. This was a little bit challenging for some of you when we went over end behavior earlier this year. However, the easiest thing for you to do when I'm asking for end behavior is to automatically put, as x approaches infinity, f of x approaches blank, do a line like that. So because this is what I'm asking you for, is the end behavior. What is y doing as x is approaching infinity? And as x approaches negative infinity, f of x approaches blank. And so when I have an even power and a positive coefficient. So what this means is that my coefficient, or my a value, is positive, so it's f of x equals positive a, and then x to an even number. So I have a positive coefficient and an even exponent, or I could even do f of x equals x squared. So I have a positive 1 is my coefficient, and my power is 2. I can graph this to help me find my end behavior. So I'll graph it, my parabola. So as x approaches infinity, or as this is approaching infinity here, remember this is my x-axis, this is my y. So as x is approaching infinity, my y is also approaching infinity. And as x is approaching negative infinity, or if I'm moving toward infinity in the negative direction, notice that f of x is also approaching infinity here. So it's approaching infinity in both directions. So my rule for this, for an even power and a positive coefficient, so whenever I have anything that has an even power and a positive coefficient, so let's say I have f of x equals 80x to the 6, I know my end behavior will be as x approaches infinity, f of x approaches infinity, and as x approaches negative infinity, f of x will approach infinity as well. So this is the rule for this type of function. So when I have an even power and a negative coefficient, so let's just do the opposite of this. So I have f of x equals negative x squared. This is a transformation, right? You guys are used to doing this. So this is an x-axis reflection, which means that I'm reflecting it across the x-axis facing down. So here I'm trying to describe my end behavior. I don't want to get too bogged down with the graphing. This is just used to help me figure out through Sketch what my end behavior is going to be. So as x approaches infinity, f of x approaches negative infinity. And as x approaches negative infinity, f of x also approaches negative infinity. And I know this, so if I'm going across my x-axis towards positive infinity, I can see that my y values are slowly approaching negative infinity, so they're going down. And as x is approaching negative infinity, or moving in the negative direction, my y values are also decreasing there. And so this is always going to be the rule. So as x approaches infinity, f of x approaches negative infinity, and as x approaches negative infinity, f of x approaches negative infinity. This will always be the rule for this type of function. So for example, if I have f of x equals negative 13x squared, it's still going to be this type of end behavior for that graph. So now let's look at odd powers. So if I have an odd power with a positive coefficient, so let's just keep it simple. We'll do f of x equals x cubed. Look at this. So we're finally getting a little bit of difference here. As x approaches infinity, so as x is approaching infinity, my f of x value is also approaching infinity. And as x approaches negative infinity, f of x also approaches negative infinity. So as I'm moving this direction, so I'm moving this way, my y value is approaching negative infinity. And this will always be the rule for an odd power with a positive coefficient. So this will be the same thing with 2x to the 7th. This will be my end behavior that I'll be using. Our last example is an odd power and a negative coefficient. So I'm going to do the same thing as I did up here, but for the cubic. So f of x equals negative x cubed. So this, remember, is my transformation. I'm flipping it over the x-axis. So I'm doing an x-axis rotation. So I'm pretty much going like this, flipping this down here and this up to here. So it's going to look something like this. And so I'm reversing my end behavior here. So this is, remember the way that I write it. I can write it as x approaches infinity, and as x approaches negative infinity, f of x approaches negative infinity here. So I'm looking at x moving in the positive infinity direction, and my y value is approaching negative infinity. And as I'm looking at x moving in the negative infinity direction, my y is doing what? It's approaching positive infinity. And so this will always be the rule for an odd power with a negative coefficient. So even if it's f of x equals negative 3x to the 13th, that will be the rule for the end behavior for that. So let's do a couple of examples using our knowledge of parent functions and graphing. We're going to start doing some domain and range stuff, get back into increasing and decreasing intervals. Then we're going to describe the symmetry and then the end behavior finally. So we're looking at this function 3x to the 6th. So this is an even power and a positive coefficient. So I can automatically fill this in using the rules that I just did before. So I know that it's positive power and an even coefficient. So I know that this is going to be infinity and infinity. It's an even power, so I know it's going to be symmetrical about the y-axis. And so everything else I can kind of do with graphing. So this is going to look a little bit different than my x squared graph because I've got a couple of different transformations going on. First of all, I know it's going to be significantly skinnier because my power is much higher. So just like x to the 4th is a skinnier graph than x squared, x to the 6th is also going to be skinnier. And then I'm going to be doing a vertical stretch by 3 also. So I'm just going to continue to make it skinnier and skinnier. So it's going to look something like this. And just because we're just starting this, it doesn't have to be perfect. I'm not going to be asking for any intercepts or any specific points at this stage of learning. So we're just reviewing. So just a quick sketch. I want you to show me that it's skinnier than the x squared. I want you to show me that my y values are greater than or equal to 0 here because I have an even power. And so the way that I would describe that using domain and range, remember domain are my x values. So what are all my possible x values here? Well, they're all real numbers. So if you look, this arrow is slowly extending toward all x values in the positive infinity direction, and it's extending toward values, all x values in the negative infinity direction. So my domain is all real numbers. But like I just said, I'm not going to have any negative y values. So for this, I'm going to have it y is greater than or equal to 0. So that's going to be my range. So y can be any real number that's greater than or equal to 0. My increasing interval, so this is a throwback a little bit to our graphing unit. So my increasing interval, this is asking me where is the graph increasing? And it's increasing here from my absolute minimum at 0, 0. It's increasing from 0, 0 to infinity. So if you remember the way that I write this is that I write it as 0, infinity. So I'm just using my x values. So at x equals 0 to x equals infinity, or x is less than infinity. So that's my increasing interval. This is where it's increasing. The opposite of that is decreasing. So you can see my graph here, the y values, as the x values move closer to 0, my y values are decreasing here. And so that's going from negative infinity to the point 0, 0 as well. So from x is greater than infinity to x equals 0, my graph is decreasing. So that's the first example. The second example that I want you guys to outline with me is a negative coefficient and an odd exponent. So this was the last one that we did, the last example that we did right before we started these examples. And so when I have an odd power and a negative coefficient, remember that as x approaches infinity, f of x approaches negative infinity. Let's see if I can write this in this tiny space. And as x approaches negative infinity, f of x approaches positive infinity, because this is the reverse of my cubic. When I have an x-axis reflection here, that's my transformation. I'm going to be rotating the graph from the normal shape that looks like this, where as x approaches infinity, f of x approaches infinity as well. I'm rotating it in the other direction. I'm reflecting it over the x-axis. And so if we look at our other points here that can give us clues to how to describe this, I have an odd power. So remember my odd power rule, my symmetry is about the origin. So I have origin symmetry or odd power symmetry. So I can write those descriptors in right away. So again, because it's an odd power, I know it's going to have that kind of S shape like that. Because it's a quintic and not a cubic, I know it's going to be skinnier. I know it's going to be, so this is going to be skinnier than x cubed. I also have a vertical stretch here, which makes it even closer to the y-axis, so even skinnier there. And I have an x-axis reflection. So it's going to be reversing the direction of those arrows. So this is going to be closer to the y-axis like this, and it's going to be going in the other direction as my positive parent quintic function. And so my domain here, I have all real numbers. My range here, again, all real numbers. So I have all y values and all x values accounted for here. And then I can describe my increasing and decreasing intervals. So if I'm looking here, as I'm moving from left to right, so move left to right for intervals. As I'm moving left to right, is there any point where my graph is increasing? My answer is no. So I don't have any increasing intervals. So the only interval I have is decreasing, and so that's going from negative infinity to positive infinity. And remember, these are only my x values. So a lot of you put in y values here on your quizzes several units ago, several topics ago, but when I'm describing my intervals, it's only x values. So intervals are only x values. Okay, so our last example that I'm going to go over involves not just a negative coefficient and an exponent. It's a little bit erased here, but it's also a fraction. So it's kind of hard to see the sun is coming in, which is so nice. So if I look here, I know that I have a negative coefficient and a positive exponent. So that's the second rule that I covered. So my end behavior as x approaches infinity, I know f of x is going to approach negative infinity based on the rules that I wrote before. And I'll go over this again when we graph this out. So as x approaches negative infinity, f of x approaches negative infinity, just from what we did with the rules before. It has an even power exponent, so my symmetry is about the y-axis. And I know that it's going to be skinnier than x squared because my y values are going to be higher. My y values are going to be greater than they would be for the same value of x if I was to put in x squared. Remember, if I have x equals 2, 2 squared is 4, but 2 to the 4th power is 16. So that y value is much greater than 4. It's exponentially greater than 4. I also have a vertical compression. So this is going to be making it flatter, but not by too much. And then I have an x-axis reflection here. So I'm reflecting it over the x-axis. So it's going to look something like this. And if you want to, if you feel the need to, you can plug in specific values for x, like 1. So 1 to the 4th is 1, and then times -1/2. So x equals 1 and x equals -1. I'm going to have y equals -1/2. If you want that for easier graphing, feel free. My domain here, it incorporates all x values, so my domain is all real numbers. But my range here is different than it was before because now y values, because I have an x-axis reflection, my y values are all less than or equal to 0. So y is less than or equal to 0 here. My increasing interval also changes because of the x-axis reflection. So if I'm reading it left to right, remember intervals read left to right, x values. So left to right, I'm increasing here from x equals -infinity, or x is greater than -infinity, to this point 0, 0. So my increasing is from -infinity, ooh, that's gross looking, -infinity to 0, and my decreasing goes from 0 all the way to +infinity. All right, so that's how I sketch these graphs and then describe them. And again, I'm not going to be asking for any specific intercepts or points, but if you want to, you can solve the function by inserting specific x values to get your graphs to be as specific as possible. So the last thing that I want to go over is power functions with a negative exponent. And while I'm gone, what I really want you guys to do is use Desmos. So Desmos, or your graphing calculator, to really figure out what these are going to look like. So we already know our first function, our first power function with a negative exponent, or f of x equals x to the -1. And remember, when I raise something to a negative exponent, it's the same as taking the reciprocal. So I'm putting a 1 over x to the first power here. And so this is called a reciprocal function. So when I f of x equals x to the first is the same as 1 over x, and this is called a reciprocal function. And we've graphed this parent function, f of x equals 1 over x, and it looks something like this. So if I actually drew it nicely, it would look a little bit more like that. And remember that it approaches but never touches, never reaches this x equals 0. So it's undefined at x equals 0, because if x equaled 0, this whole function would be undefined. And the way that I graph that is that I have this vertical asymptote, or this area, so this vertical asymptote is what it's called, at x equals 0. And this is the point, this is the line that it's reaching, or it's approaching, but it's never reaching, and it's my undefined value for x. So my domain here would be that x does not equal 0, but x can be any other number besides that. And so what I'm going to have you do with these is graph specific power functions with negative exponents. And the first one that I'm going to have you do, I'm going to write out the function and what it means, but I want you to go through and try these out with Desmos and graph them, just so you can start seeing what they look like. And so the first one that you're going to be doing, let me erase this. The first function that you're going to be looking at is f of x equals 4x to the -2. And remember that this is the same as 4 times 1 over x squared, because x to the negative 2, using my negative exponent rule, this is the reciprocal of x squared. So it's 1 over x squared. And so I know several things just looking at this. I know that this is always going to be a positive number because I have an x squared associated with it. I also know that x will never be able to equal to 0. So this is the same as 4 over x squared, right? 4 times 1 over x squared is the same as 4 over x squared. So I know that it's always going to be positive. So y is always positive, so y is greater than or equal to 0. And I know that x cannot equal 0 here. So these are two things that I know right away looking at this function. So if I put in any negative number for x, it's still going to give me a positive y because I have a square there. I have a power of 2 there, an even power. And so if I was to graph this, and I'm just going to do a quick sketch here because I want you to be doing this on Desmos. I'm going to have my reciprocal function, but it's going to look something like this. And so when I have these even powers, or these even negative powers, because it's always, the function value is always going to be positive, I'm not going to be having, unless it's a negative coefficient, I'm never going to be having any values in this lower half of the graph, so for negative y's. And so again here, my range is that y is greater than or equal to 0. My domain, or my x values, x does not equal 0, but it can be equal to anything else. And then if you can, I would love for you to start thinking about what's my increasing and my decreasing intervals here. What's my symmetry? What's my end behavior? So, and these follow the same rules that we did before. So I have an even exponent here, so my symmetry is about the y-axis. And you can see that this is true because from here to here, it's symmetrical. My end behavior is I have a positive coefficient and an even power. So as x approaches infinity, and as x approaches negative infinity, I can solve this. It's going to be a little bit different than it was before because now I also, with my range restriction, I also have a horizontal asymptote, or I have pretty much a wall that's built up here that's preventing me from getting to numbers below 0. So as x approaches infinity here, I'm reading it, x approaches infinity, f of x is approaching 0. And as x is approaching negative infinity, or moving in the negative direction, my f of x is also approaching 0. And then if I'm looking at my increasing and decreasing intervals, I'm reading the graph left to right across the x-axis. So I'm using x values. So it's increasing from negative infinity, or from here, to 0. And then it's decreasing from 0 to positive infinity. So you can see here the y values are increasing until I reach 0. And then once I reach 0 and I start moving to the right, my y values are decreasing. So that's the first example. I'd love for you to do 2, 3, 4, and 5 on Desmos for homework. And I will post the answers to those online. And so I just want you to start getting in the hang of that. And your homework for this lecture, or this unit, or this topic, your homework for this topic I will hand out in class. It's homework number 1, and I'm going to have you do 1 through 3 on that homework on your own. And then I want you to use Desmos for 4, 5, and 6. So I will post those directions online. If you have any questions, please feel free to reach out. And I'll talk to you soon.